In this video, we're going to go over atomic structure practice problems. So we're going to solve a number of questions to do with atomic structure. So the first one is dealing with the issue of wavelength frequency. The second part, we get to talk about the de Broglie wavelength. The third part of the question, we get to talk about the wave number and the frequency. The third one, we get to talk about the speed of light, the frequency, which are still wave properties. We get to talk about the energy of a photon. Then we get to talk about the electron volt conversions into joules. We talk about transitioning of photons. Then we get to talk about, again, that is the Broglie wavelength. So calculate the number of photons having a wavelength of that. So this is also trying to assess our understanding of our wave properties. Question 11 is from Heisenberg's uncertainty principle. Question 12 is transition. Question 13 is quantum numbers. Question 14 is quantum numbers. Question 15 is coming from energy of a photon. So these are the questions that are going to help us understand the different questions that you may be asked under atomic structure. So let's get started. The color orange within the visible light spectrum has a wavelength of about 620 nanometers. What is the frequency of orange light? So we need to understand that when you're talking about wavelength and frequency, these two are inversely proportional, meaning that as you get to increase frequency, on the other part, wavelength is going to be decreasing. So this is the equation that we get to look at when we are trying to understand the relationship between the frequency and the wavelength. So what do they want us to find? They want us to find the frequency. So it's going to be the speed of light, which is 3 by 10 to the power 8, that's in terms of meters per second, divided by the wavelength. So what is our wavelength in this case? 620 nanometers. So whenever you're dealing with our calculations, we need to make sure that the units are standard. So we need to convert the nanometers to meters. So the easiest way of converting is just by dividing by 10 to the power 9, which is the same as multiplying by 10 to the negative power. So that is now in meters. So we have 620 by 10 to the power negative 9 meters. Okay, so now let's try to calculate to see the frequency that we're going to have in such a case. So we have 3 by 10 to the power 8 divided by 620 multiplied by 10 to the power negative 9. Okay, so what I'm getting as the frequency in this case is actually 4.84 by 10 to the power 14 Hertz. Okay, so if you check in the question, the value that we've been given is only 620, which is actually two significant figures only. So our answer can be 4.8 by 10 to the power 14 Hertz. The second question, the speed of an electron is about 1.68. So right there, that was supposed to be a power there. So it's supposed to be 1.68 by 10 to the power 8 meters per second. So that is the speed of an electron. What is the wavelength? So we asked to find the wavelength given the speed of an electron. So this takes us to what we call de Broglie wavelength. So de Broglie wavelength requires us to understand that wavelength can be given as Planck's constant divided by momentum, where we know that momentum is a product of mass and velocity. So this comes from the relationship of wave-particle duality, which implies that a photon behaves as a wave as well as a particle. So this is a combination of Einstein's famous equation and also the energy of a photon. So if you combine these equations, this is what it's going to give you, which is called de Broglie. So de Broglie is the one who combined the equation and he came up with this simplified equation. So Planck's constant is 6.626 times 10 to the power negative 34. Then the mass of an electron is also known. It's a constant that is known. So the mass of an electron is 9.11 times 10 to the power negative 31 kilograms. Okay, multiplied by the velocity in this case, which has been given in the question to be 1.68 times 10 to the power 8. Okay, so you can get your calculator there. So I'll start first of all by multiplying what's in the denominator there. Okay, so 9.11 times 10 to the power negative 31 multiplied by 1.68 by 10 to the power 8. Okay, so now I'll divide what I'm getting into the 6.626 times 10 to the power negative 34. So after dividing, what I'm getting is 4.32. So our wavelength is actually 4.32. So 4.33 by 10 to the power negative 12 meters. So if you want this to look better, since this is a small value, you can take it to smaller units so that it looks bigger. So you can multiply by 10 to the power 9 to convert it to nanometers. Okay. So what I'm getting after multiplying by that in standard form, scientific notation, so it's 4.33 times 10 to the power negative 3 nanometers. So that is our wavelength in this case. Okay. The third question. Calculate the wave number and the frequency of a violet radiation having a wavelength of 3,500 angstroms. Okay, so what basically is a wave number? So you need to know that a wave number denoted by that is actually just 1 over what? The wavelength. So if you're given the wavelength, you're able to find what? You're able to find the wave number. Okay, so how do you get to do that? So in this case, we've been given our wavelengths to be in angstroms. So you need to know that 1 nanometers is equal to 10 angstroms. Okay. But then we need to know that whenever we're working with a wavelength, whenever we're doing calculations with anything, you need to make sure that they are in standard or the SI unit. So the standard of measuring length is meters. So we need to convert the angstroms to meters. So 1 nanometers is actually equivalent to what? It's equivalent to 10 to the power negative 9 meters. Okay. So then that is equivalent to 10 angstroms. So in this case, how many angstroms do we have? We have got 3,500 angstroms. So we can multiply that. So 3,500 multiplied by 10 to the power negative 9 divided by a 10 there. Okay. So what basically are we getting there? So we have 3.5 by 10 to the power negative 7 meters. Okay. So we've converted our angstroms to meters. So you can now plug in that we have there. So basically that is actually a negative there, negative 7. So our wave number is going to be 1 over 3.5 by 10 to the power negative 7. Okay. So I'm getting 2.85 or 2 point, let's just make it 2.9. Okay, 2.85, 2.86 by 10 to the power negative to the power 6. Okay, so basically when you're looking at the units of wavelength there, it was meters. So it's obviously going to be meters negative there for our wave number. Okay, question 4. Or getting back to the previous question, there's another part which is saying the frequency as well. We need to determine the frequency. Okay, so what did we say? We say the frequency is actually inversely proportional to what? To the wavelength. So therefore, our frequency is inversely proportional to what? To our wavelength. So in this case, we have our wavelength. So our speed of light is 3 by 10 to the power 8. Then what have we determined to be our angstroms in meters? So we said you multiply the 3,500 by 10 to the power negative 9 and get to divide by 10, which gave us 3.5 by 10 to the power negative 7. So if you get to divide that into the speed of light, what basically are you going to get? So 3 by 10 to the power 8 divided by that. Okay, so what we have as our frequency is 8.6 times 10 to the power 14 is. Question 4. Calculate the wavelength of light that has a frequency of 5.2 by 10 to the power 12. Okay, so the speed of light has been given to be 3 by 10 to the power 8. So we are asked to calculate the wavelength. So again, we need to understand and appreciate the fact that whenever you're talking about wavelength, what are we trying to say? So we're trying to say wavelength is actually inversely proportional to the frequency. So the speed of light 3 by 10 to the power 8. The wavelength is what? The frequency in this case has been given to be 5.2 times 10 to the power 12. So divide that. So we have 3 by 10 to the power 8 being divided by 5.2 times 10 to the power 12. Okay, so what we have is 5.77 times 10 to the power negative 5 watts. So this is in meters. Okay, so because our units were standard. Okay. Okay, so the next question says, calculate the energy and the wavelength of a photon of light with frequency that. Okay, so we want to calculate the energy and the wavelength. What have we been given? We've been given the frequency. So we need to understand that the energy of a photon is given as a product of Planck's constant multiplied by what? Multiplied by the frequency. Okay, so what can we start with? Have we been given the frequency? Yes, we've been given. So we can find the energy of a photon. So the energy of a photon is going to be, the Planck's constant is 6.626 times 10 to the power negative 84. Then our frequency in this case is 6.165 times 10 to the power 14. So get your calculator there and plug in the values that we have there. So I'll start with 6.165 times 10 to the power 14 multiplied by 6.626 times 10 to the power negative 84. Okay, so what I'm getting is 4.08 times 10 to the power negative 19. That is in joules. Okay, so basically what we've gotten there is our energy of a photon. So we also need to determine now the wavelength. So basically we know that the wavelength is actually inversely proportional to what? To the frequency. Okay, so the wavelength is going to be the speed of light divided by what? Divided by the frequency. So our speed of light is 3 by 10 to the power 8. Our frequency has been given to be 6.165 times 10 to the power 14. Okay, so 3 by 10 to the power 8 divided by 6.165 times 10 to the power 14. What I'm getting is as our wavelength is 4.87 times 10 to the power negative 7 meters. Question 7. The electron volt is a convenient unit of energy for expressing atomic scale energies. It is the amount of energy that an electron gains when subjected to a potential of 1 volt. So 1 electron volt is actually been given to be a constant there. So 1 electron volt, it's 1.602 times 10 to the power negative 19 joules. Okay. So using the Bohr model, determine the energy in electron volts of the photon produced when an electron in a hydrogen atom moves from an orbit of n is equal to 5 to n is equal to 5. So this is coming from transition of electrons. So basically an electron volt is used to represent very, very small amounts of energies, which can be very difficult to understand. Okay, so we need to understand that from Bohr's model, the energy of a photon or energy involved in transition is calculated from this formula, negative 2.178 times 10 to the power negative 18, then 1 over n final squared minus n initial squared. Okay, so in this case, if you look at our final one, which one is our final? So we can plug in there. So if you look at that part, which one is our final? I'm moving from n is equal to 5 to n is equal to 2. So we can plug in. So our final one is what? Our final one is 2 squared. Our initial is 5 squared. Okay, so you can get your calculator there and see what we're going to have. So negative 2.178. So I can start with first what's in the brackets there. So 1 over 4 subtract 1 over 25. So 1 over 4 subtract 1 over 25. So multiply by negative 2.178 times 10 to the power negative 18. Okay. So basically what I'm getting is a negative 4.57 times 10 to the power negative 19 joules. So these things are very easy for you to follow up. So if you're getting confused in which one to start with when it comes to this part, just make sure that you understand what it is. So whenever you have an electron moving from an higher energy level to a lower one, there is loss of energy, so you expect your solution to be a negative. And when you're moving from a lower energy level, when an electron is moving from a lower energy level going outside, it's going to gain more energy, because we know that the are the principal quantum number, the are the energy of electrons contained in that energy level. Okay, so this is our energy in joules. So we want to convert them to electron volts by using the ratio that we've been given there. Okay, so what have we been told? We've been told 1 electron volt is equivalent to that amount of energy. So you can put that negative 4.57 times 10 to the power negative 19 joules. Okay, so basically we're just supposed to divide by the 1.6. So divide by 1.602 times 10 to the power negative 19. Okay, so basically what I'm getting as our value in electron volts is, so we have negative 2.856 times 10, or we can just put it this way. So what we have is negative 2.86 electron volts. So that's our answer in electron volts. Okay. Question 8. The so-called Lyman series of lines in the emission spectrum of hydrogen corresponds to transitions from various excited states to the n is equal to 1 orbit. Calculate the wavelength for the lowest energy line in the Lyman series to 3 significant figures. In what region of the electromagnetic spectrum does it occur? Okay. So it's very important for us to understand what we are talking about here. Okay. So we have what we call transitions of electrons. Okay. So whenever you're having transitions of electrons from other energy levels getting to the first one. Okay. So these are called Lyman series to start with. Okay. And the electromagnetic spectrum associated with this is actually the ultraviolet. Okay. Then the second one, coming from other energy levels, getting to the second one, they're referred to as Balmer series. Okay, and anything associated with that is said to be what? It's actually the visible light that is associated with the Balmer series. Then the third energy level, okay, you get the bracket. The other one, it's the pass chain. Then number 5 is P-fund. So all the others going up is infrared, the last 3. But for the first 2, the first one is ultraviolet in terms of electromagnetic spectrum. Okay, so now let's try to get to answer the question. So we are saying calculate the wavelength of the lowest energy Lyman series. So remember, we are saying that under Lyman series, if we are talking about transitions associated with the first energy level coming from the other ones outside. So obviously the lowest one or the closest one is going to be from the energy level 2, because others are coming from outside. So we'll talk about transition from 2. Okay. Then the highest or the maximum comes from the infinity. Okay, because if you talk about, basically, in real sense, if you're talking about a hydrogen atom, it only has an electron in the first energy level. So basically when it's lost, it goes to the infinity, or it's never ending. So that's the maximum. So in terms of the lowest, we'll talk about the next energy level, which is the second one. Okay. So we are trying to predict now. So calculate the wavelength of the lowest energy line. Okay. So we said whenever you are dealing with the wavelength calculations, when you're dealing with transitions, without wasting much of your time, you can just go to what we call Lyman's constant. So Lyman came up with a formula that helps us to do that. So it's 1 over wavelength being equal to Lyman's constant. Then we apply the same there. Okay. So in this case, what are we trying to find? We're trying to find the wavelength. Okay, so 1 over wavelength is equal to, so Lyman's constant is usually given in centimeters, which is 109,677 centimeters. Okay, then what was the initial? So we are saying for it to be the lowest energy line, we are saying it's coming from n is equal to 2, getting to n is equal to 1, because anything associated with 1 is Lyman series. So now the lowest one is going to come from the second one. Okay. So the initial one, where is it coming from? It's coming from 2. Okay. So say 1 over 2 squared minus, then which one is the initial there? Okay, so the initial is actually getting to 1. Okay. So after doing your calculations, what do you get there? So obviously when you look at what we have in the bracket, say it's going to be a negative, and we don't want to find a wavelength that is negative, so you can put a negative there. Okay, so we have 1 over 4 subtract 1 multiplied by a negative 109,677. Okay, so we have 1 over wavelength. What I'm getting this side is 8.225775 times 10 to the power 4. Okay, so we're trying to find the wavelength, so it's supposed to make the wavelength the subject of the formula. So the moment you make the wavelength to be the subject of the formula, it's going to be the reciprocal of what is on the right hand side. So our wavelength is going to be 1 over the 8.225 times 10 to the power 4. So if you divide that, basically what you're going to have as your answer is 1.216 times 10 to the power negative 5. So that's in terms of meters. So we want to make our answer come out and make a bit sense. So what we have is 1.216 times 10 to the power negative 5 meters. So if you've seen that when you're using a bigger unit and you're using the answer seems to be lower, take it to the lower unit so that you have a bigger figure. So let's take it to nanometers. So you take it to nanometers by multiplying by 10 to the power 9. Okay. So we have 1.216 by 10 to the power negative 5. Then we're trying to take this to nanometers. We multiply by that 10 to the power 9. So we have 12,156.9 nanometers. Okay, so that looks better. Okay, so what basically we have here is supposed to be in centimeters. Okay, because the Lyman's constant that we're talking about is in centimeters. It's 109,677 centimeters. So our answer is in centimeters. So that being in centimeters, for us to take it to meters, we're supposed to do what? We're supposed to divide by 100, which would be 1.216 times 10 to the power negative 7 meters. And converting that to nanometers, we're supposed to multiply by 10 to the power 9, which is going to cancel out the negative 7 and remain with the power 2. So it will be 1.216 times 10 to the power 2 nanometers. So multiplying by 10 is 100, which is going to be 121.6 nanometers as our final solution to the question. Okay, question 9. An electron of mass 9.11 times that moves at near the speed of light using a velocity of that. Calculate the wavelength. Okay, so in such a case, what we're trying to deal with here is what we call the Broglie wavelength. Okay, which we've talked about under wave particle duality in the area question. So you can try it out because we've talked about it. So the wavelength, or the Broglie wavelength, is given as Planck's constant divided by the momentum, which is a product of mass and velocity. So we have 6.26 times 10 to the power negative 34 divided by, what is our mass? Our mass is 9.11 times 10 to the power negative 81, and our velocity is 3 by 10 to the power 8. Okay, so we'll start with the denominator to make it easier. 9.11 times 10 to the power negative 81 multiplied by 3 by 10 to the power 8. So when we're trying to divide that into the Planck's constant, okay, so the value that I'm getting of our wavelength is 2.42 times 10 to the power negative 12. So what units are we going to use here? So we're using meters. Okay, so even this one you can multiply it by 10 to the power 9 to convert to nanometers. Okay, so taking it to scientific notation, it's 2.42 times 10 to the power negative 3 nanometers. Alright. Question 10. Calculate the number of photons having a wavelength of 10 micrometers required to produce energy of 1 kilojoules. Okay. So the number of photons. So an energy of a photon, a single photon, is given as a product of Planck's constant and the frequency. So we also know that the frequency is given as inversely proportion to the wavelength. So it's c over what? The wavelength there. So what have we been given? So we know Planck's constant is 6.626 times 10 to the negative 34. The speed of light is 3 by 10 to the power 8. Our wavelength there has been given in micrometers. So micro means 10 to the power negative 6. So it's same as 10 to the power 10 times 10 to the power negative 6 meters. Okay. So let's try to do the calculations there. So what we have is 6.626 multiplied by 10 to the power negative 34 times 3 by 10 to the power 8. It's being divided by 10 times 10 to the power negative 6. Okay, so what we have is the energy of a single photon is 1.999 times 10 to the power negative 20 joules. That's what we have. Okay, so what is the energy of a single photon? So now that we found the energy of a single photon, how do we get to find now the number of photons that are required to give us that amount of energy? Okay, so one photon is giving us 1.99 times 10 to the power negative 20 joules. So how many photons are required to give us 1000 joules? Because 1 kilojoules means 1000. So it's basically just trying to divide it into 1000. So if you divide our answer into 1000, what we have is our value of x is going to be 5 by 10 to the power 22 photons. So that's the number of photons that are required to produce that amount of energy. So that is a very, very big number. Okay. Question 11. So this is coming from Heisenberg's uncertainty principle. Okay. So the uncertainty in the momentum of a football thrown by Tom Brady during the Superbowl traveling at 40 meters per second is 1 by 10 to the power negative 6 of its momentum. What is the uncertainty in position given that the mass is that? Okay, so according to Heisenberg's uncertainty principle, the change in position multiplied by the change in momentum is greater than or equal to Planck's constant divided by 4 pi. So Eisenberg usually, according to his principle, he made a point to say that whenever you're talking about photons, electrons, things of smaller masses, it's either you know more about its position or more about its velocity. Okay, so it's either you know more about its momentum in this case or more about its position. So more precisely, the position is known, the more uncertain you know about the momentum. Okay, so that's the way it works. So the more you know about the position, the less you know about the momentum. That's what he came up with. So in this case, they're trying to tell us to say that the uncertainty in the momentum is 1 by 10 to the power 6 of its momentum. Okay, so this is representing the uncertainty in momentum. That is the uncertainty in what? In position. So they've told us that the uncertainty in the momentum is given as what? Is actually 1 by 10 to the power negative 6 of its momentum. So we need to find the momentum so that we find the uncertainty in its principle. The uncertainty in momentum. So what is the momentum? So momentum is the product of mass and velocity. So what is our mass in this case? 0.4. What is our velocity? 40. So from there we're able to find the uncertainty in what? In the momentum. So we have 1 by 10 to the power negative 6 multiplied by 0.4 multiplied by 40. So what I have is 1.6 times 10 to the power negative 5. So that's the uncertainty in terms of the momentum. So what is the question asking us to find? What is the uncertainty in the position? Okay, so position is change in x. So if you make it a subject, so if you divide both sides by the change in momentum, the uncertainty in momentum is going to be h over 4 pi multiplied by the uncertainty in what? In momentum. So all we have to do is just get to plug in the values that we have, and we'll be able to get our solution there. So our uncertainty in position is going to be given as a Planck's constant is 6.626 times 10 to the power negative 84. Then we have 4 pi being multiplied by the uncertainty in momentum, which we've determined to be 1.6 times 10 to the power negative 5. Okay, so you can grab your calculator there and do the computations there. So 6.626 times 10 to the power negative 84 divided by 4 pi multiplied by 1.6 times 10 to the power negative 5. Okay, so therefore our uncertainty in the position is basically 3.3 times 10 to the power negative 30 meters. So that's it for this question. Question 12. Calculate the wavelength for the transition of n is equal to 4 to n is equal to 2, and state the name given to the spectroscopic series to which this transition belongs. So we said whenever you're moving from any other energy level getting to n is equal to 2, we said it was a Balmer series. Okay, so already we've answered that question. It's Balmer series. So calculate the wavelength for the transition. So this is getting us to Lyman's constant, where we are saying 1 over the wavelength is actually Lyman's constant multiplied by 1 over that n1 initial minus. Okay, so we have 1 over our wavelength. Lyman's constant is in centimeters, which is 109,677. Okay, so what do we have there now? So what we have is, what was the initial one? Initially it was coming from 4, so it's 1 over 4 squared minus the initial. Okay, so 1 over 2 squared. So basically there's a negative here that I've forgotten again, so there's a negative. Okay, so if you do your computations there, right, you have 1 over 16 subtract 1 over 4 being multiplied by the 109 677. Okay, so we have 1 over wavelength being equal to negative 2.056 times 10 to the power 4. It's basically a positive value there. Okay, so you finding the wavelength will require you to find the reciprocal of that. So divide that into the 1. What are you going to have? Okay, so what you have is a 4.86 times 10 to the power negative 5. So remember this is in centimeters because of the Liebig's constant. So therefore our wavelength is equal to, so you want to convert it to meters, or basically take it even to nanometers so that it makes more sense. So multiply by 10 to the power 9. So in this case it's going to be multiplied to the power 10 because it's in, so let me just take it to meters by just okay, so 4.86 times 10 to the power negative 5. So if you're moving from centimeters going to meters, what are you supposed to do? You're supposed to divide by 100. So after dividing by 100, we multiply by 10 to the power 9 again to convert it to nanometers. Okay. So basically we have 486 nanometers as the wavelength in this case. Question 13. What values of the orbital quantum number or angular momentum and magnetic quantum numbers are allowed for the principal quantum number n is equal to 3? So there are some basic things that we have to understand whenever we're dealing with quantum numbers. So we need to understand that we have what we call the principal quantum number, which is denoted by n. Okay, so what is the principal quantum number? So the principal quantum number tells you the energy level that you're talking about. So if you say n is equal to 1 as a principal quantum number, you're saying that you're dealing with the energy level number 1 when it comes to the structure of an atom. So in this case, what we've been told the principal quantum number is 3. So it gives you the energy and also the energy level that you're trying to talk about. Okay, so now the question is, how many orbitals are allowed for n is equal to 3? So the next energy level that we have to understand, or the next quantum number that we have to understand, is the angular momentum quantum number denoted by L. So this one is given as from 0 to n minus 1. So in this case we have 0 to all the way up to 2. So the values of L that we're going to have will be 0, 1, and 2. So the angular quantum number or angular momentum quantum number actually represents the shape of the orbital that you're talking about. So we have the S, the P, and the D. Okay. Then so the question, so we're already answering the question, because the question is saying what values of the orbital quantum number or angular momentum quantum number and magnetic quantum numbers are allowed. So these are already the angular momentum quantum numbers. So now we also have what we call the magnetic quantum numbers. So the magnetic quantum numbers gets to be dependent on each value of the angular quantum number. So I'll start with L is equal to 0. So when L is equal to 0, what is our angular of our s orbital? So we have ml. So it moves from, so the formula that we use when determining the magnetic quantum number is from the negative L to the positive, to its positive. Okay, so it's a range. So there's no negative and positive or 0, so we just have 0 there. So what you need to know is that the magnetic quantum number actually tells you the number of orbitals that a certain angular momentum quantum number can have. So if you're talking about s orbital, it only has a single orbital, meaning that it can only have a maximum of 2 electrons. So that's the value of the magnetic quantum number for L is equal to 0. If you go to L is equal to 1, our ml, we are saying, is moving from its negative to its positive. So we have negative 1, we have a 0, and the 1. So there are three what? There are 3 orbitals under L is equal to 1. So this is able to have 6 electrons. Then the last one, L is equal to what? L is equal to 2. So from -2, so these are the values of the magnetic quantum number. So there are 5. This explains why there are 10 electrons in the p or in the d energy level or the d orbital. Okay, so the question is how many orbitals are allowed. So the orbitals are determined by the magnetic quantum number. So let's count the magnetic quantum numbers that we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So it's basically 9 as our solution. Okay. Question 14. Give the name, magnetic quantum numbers, and number of orbitals for each sublevel with the following quantum numbers. So we are trying to give the name, the magnetic quantum numbers, and also the number of orbitals. So the number of orbitals is determined by the number of magnetic quantum numbers. So I'll start with A. So for A, we have our principal quantum number to be 3, and we're interested in L is equal to 2. So this is a restriction, unlike the previous question. Okay, so for L is equal to 2, we say the magnetic quantum number is moving from its negative to its positive. So it's from -2 up to its positive. So these are the allowed magnetic quantum numbers. And the name given to this angular quantum number, that shape, L is equal to 2, is what? It's a D. So it's a D orbital. So 10 electrons. So now, number of orbitals is given by counting the number of what? Magnetic quantum number. So it's 1, 2, 3, 4, and 5. So we have 5 orbitals for A. Going to B, we have N is equal to 1. Then L is equal to 0. So for L is equal to 0, we don't have its negative and positive. So we only have a single magnetic quantum number to be 0 there. So how many orbitals does it have? It has got a single orbital. So 1 orbital. And the name is the S orbital. Okay. Okay. Question 15. The blue color of the sky results from a scattering of sunlight by air molecules. Blue light has a frequency of about 7.5 times 10 to the power 14 Hz. Calculate the energy of a single photon associated with this frequency. B. Calculate the energy of more photons with this energy. C. Would the energy be sufficient to break the chlorine to chlorine bond in chlorine molecule? The average bond enthalpy is what? Okay, so we can go back to the start of the question. So we've been told that the frequency is what? So we have a frequency being equal to 7.5 times 10 to the power 14 Hz. So the first question is to say, calculate the energy of a single photon. So we've said that the energy of a single photon is given as a product of Planck's constant and the frequency. So Planck's constant is 6.626 times 10 to the power -84. In this case, our frequency is 7.5 times 10 to the power 14. So you can grab your calculator there. 6.626 times 10 to the power -84 multiplied by 7.5 times 10 to the power 14. Okay, so what we have as our solution in this case, we have 4.9695 times 10 to the power -19 joules. Okay, so what is the energy of a single photon? Second part of the question says, calculate the energy. So this is our A. Calculate the energy of a mole of photons with this energy. So whenever we're dealing with number of moles of any particles, we need to appreciate the use of the Avogadro's constant. Okay, so which is 6.022 times 10 to the power 23. So the units are anything that you have per what? Per mole. So in this case, it will become photons per mole. That's what it means. That's Avogadro's constant. Okay, so what are we trying to say? Calculate the energy of a mole. Okay, so this energy that we've calculated is joules per photon, it's per single photon. So if we multiply by the Avogadro's constant, what are we going to have? So we're going to have 6.022 times 10 to the power 23. So I said the units for Avogadro's constant goes with what you're talking about, but it's supposed to be per mole. So it's photons, in this case, per mole. It's being multiplied by 4.9695 times 10 to the power negative 9, 19. The units are joule per what? Per photon. So the photons will cancel out, and basically the units that are going to remain with will be what? Joules per mole. Okay. So multiply what we have as our solution there by 6.022 times 10 to the power 23. Okay. So the value that I'm getting is basically 2.99 times 10 to the power 5 joules per what? Per mole. So that's per mole of a photon. So we have actually a greater energy as compared to a single photon. Then the last question says, would the energy be sufficient to break the chlorine to chlorine bond in the chlorine molecule? So there the units that we have are basically in kilojoules, 242 kilojoules. So we want to do the same. We want to convert what we have in this case. Okay. So if you look at the units, in fact, that we have, let's look at in the question. The information that was given was 7.5, which is two significant figures. So this can be 3 by 10 to the power 5 joules per mole as our solution. So if you convert this to kilojoules, you're supposed to divide by 1,000. Okay, so if you divide by 1,000, you're going to remain with approximately 3 by 10 to the power 2, because 3 zeros are going to cancel out, which is basically 300 kilojoules per mole. So now if you ask yourself a question, is this enough? Is it less than or greater than the 242? So the fact that it's greater, so the fact that the energy of a mole of photons in this case is greater than the amount of enthalpy required, so we can say that therefore the energy is what? The energy is sufficient. Okay. So thank you very much for spending time to get to the end of this video. I hope it has helped you out. If you've liked the video, give us a comment, and if you'd want us to make a video on any topic, let us know in the comment section. Thank you very much.